Title: RLCoder. Reinforcement Learning for Repository-Level Code Completion. Abstract: Repository-level code completion aims to generate code for unfinished code snippets within the context of a specified repository. Existing approaches mainly rely on retrieval-augmented generation strategies due to limitations in input sequence length. However, traditional lexical-based retrieval methods like BM25 struggle to capture code semantics, while model-based retrieval methods face challenges due to the lack of labeled data for training. Therefore, we propose RLCoder, a novel reinforcement learning framework, which can enable the retriever to learn to retrieve useful content for code completion without the need for labeled data. Introduction. Code completion has emerged as one of the most important features in integrated development environments, IDEs, with the advancement of large language models for code LLMs. However, due to the vast size of code repositories and the limitations of context length in models, repository-level code completion cannot practically leverage the entire repository directly as context. Therefore, previous works typically employ a retrieval-augmented generation (RAG) strategy. In this approach, the unfinished code in the current file serves as a query to retrieve code candidates from the entire repository, providing cross-file context. These candidates are then concatenated with the unfinished code before being fed into code LLMs. Background. Retrieval-augmented generation (RAG) is an approach that enhances the quality of generation by retrieving from external knowledge bases. This method includes three key components: retriever, generator, and augmentation techniques. The retriever is used to find relevant information from a large-scale dataset or knowledge base, including pertinent documents, facts, or text snippets that are relevant to the input query or prompt. The retrieved information is fed into the generator, which integrates this external knowledge into the generation stage. Augmentation techniques focus on how retrieved information is integrated into the generation process. To formalize the RAG process, consider a scenario where we want to generate code based on a query queue and a set of retrieved candidates, C1, C2, Cn. The process can be described by the following formula. Code equals generate, queue, retrieve, queue, C1, C2, Cn. 1. In recent years, researchers have conducted a substantial amount of research related to RAG, highlighting its promising potential for future applications. Many studies have utilized RAG for code-related research. In repository-level code completion, due to the massive amount of code in the repository and limited context of generator, it is impractical to use the entire repository as the context for generation. Therefore, most current methods employ the RAG method to retrieve suitable candidates from the repository for generation. We evaluate RLCoder with extensive experiments with several LLMs on CrossCodeEval and RepoEval. Experimental results show that our framework achieves 12.2% improvement of exact match compared with previous methods. Furthermore, RLCoder demonstrates high generalizability, showing effectiveness across various LLMs and programming languages. Additionally, experiments show that RLCoder can be integrated into previous methods such as RepoCoder to enhance code completion performance further. Our main contributions are: 1. We propose RLCoder, a reinforcement learning framework for repository-level code completion. To our knowledge, we are the first to train the retriever without labeled data for repository-level code completion. Besides, we design a mechanism that uses the weighted perplexity of the target code as the reward to further enhance performance. 2. We introduce a simple yet effective split aggregate candidate construction strategy based on human programming habits. This method avoids the disruption of code continuity and outperforms fixed window candidates indicated by the experimental results. 3. We propose a stop signal mechanism to evaluate the usefulness of candidates and discard useless candidates for more effective code completion. 4. We perform an extensive evaluation of RLCoder. Experimental results show that RLCoder outperforms the state-of-the-art methods and demonstrates generalizability and applicability. We provide the code and data at https://github.com/deepsoftwareanalytics/RLCoder. The paper discusses the development of a reinforcement learning framework for repository-level code completion, named RLCoder. This framework is designed to improve code completion by learning from large-scale code repositories and leveraging both in-file and cross-file context. The authors identify limitations in current repository-level code completion methods, including the lack of labeled data, fixed window candidates, and the need for an evaluation of candidate necessity. To address these limitations, RLCoder uses a two-stage approach: training and inference. In the training stage, the authors construct data from GitHub repositories, obtain unfinished code, target code, and candidate codebase, and train the retriever, RL retriever, using reinforcement learning. In the inference stage, given an unfinished code and the current repository context, the authors use the trained RL retriever to retrieve relevant code from the codebase and then feed this context to a generator for target code generation. The paper also describes the data construction process, which includes repository filtering, dependency analysis, target code selection, and candidate construction. The authors employ a dependency analysis to identify clusters of interdependent code files and select target code segments for completion. They propose a simple yet effective split aggregate candidate construction strategy inspired by human programming habits. The RLCoder framework aims to enhance the integrity of the retrieval codebase by fusing analogy context and rationale context. It uses an iterative retrieval and generation method, involving concatenating the results generated from the previous iteration with the prior context to form a query. This query is then used for the subsequent round of retrieval and generation. Additionally, the authors highlight the importance of integrating both in-file and cross-file context in repository-level code completion. The split aggregate strategy is employed to divide code into mini-blocks based on blank lines and aggregate them into candidates. This approach ensures that each candidate's length does not exceed a preset threshold. The RL retriever training involves designing a reward mechanism, where the primary aim is to identify the optimal candidate that maximizes the likelihood of accurately generating the target code sequence given contextual information. The reward is defined as the weighted perplexity of the target code, considering the token's position and whether it's an identifier. The objective function aggregates the logarithmic probabilities of choosing each candidate. A stop signal mechanism is designed to discern which candidates to retain, ensuring only useful candidates are selected. The RL retriever is fine-tuned through a dynamic learning process, receiving rewards to update its parameters. In the inference stage, candidates are retrieved using the trained RL retriever, and the stop signal strategy is embedded to retain only useful candidates. The selected candidates are then provided as input to the generator for code completion. The experimental setup compares RLCoder with raw RAG and RepoCoder, using a dense retriever UniXcoder as another baseline. Here is a combined summary of the 2 pages. The proposed RLCoder approach is evaluated on widely used benchmarks for code completion, including CrossCodeEval and RepoEval. The benchmarks consist of Python and Java parts, with statistics shown in Table I. The evaluation metrics used are exact match, M, and edit similarity, S, which assess the precision of code completion and the similarity between generated and expected code, respectively. The experimental results are reported in Table 2, comparing RLCoder with raw RAG and RepoCoder frameworks using 5 different backbone language models. RLCoder demonstrates effectiveness on all backbone language models across the 4 evaluated datasets, with significant improvements over the corresponding best baseline models. The best performance is achieved by RLCoder DeepSeek Coder 7b, with an EM score of 30.28, improving its corresponding best baseline by 12.2% on CrossCodeEval Python and 5.1% on RepoEval. The performance trajectory curve during the training process is shown in Figure 7, illustrating the effectiveness of the training process. The M score gradually increases with each epoch until stabilizing, indicating the efficacy of the training process. The effectiveness of RL retriever, a key module of RLCoder, is assessed by comparing it with other retrieval methods, including no retrieval, VM25, UniXcoder, and UniXcoder SFT. The experimental results in Table 3 show that RL retriever consistently outperforms comparative baseline methods under all metrics in both benchmarks, underscoring its superior performance. An ablation study is conducted to understand the contributions of each component to RLCoder. The experimental results in Table IV show that removing any one component results in a performance drop, indicating that each component contributes to the effectiveness of RLCoder. The reinforcement learning mechanism is found to be the most important component in RLCoder. The research paper discusses the reinforcement learning mechanism in RLCoder, which significantly improves code completion performance. Experimental results on CrossCodeEval and RepoEval demonstrate the effectiveness of RLCoder, particularly with the stop signal mechanism. The ablation study shows that the reinforcement learning component is the most important, while other components also contribute to its performance. The generalizability of RLCoder is explored by integrating it with RepoCoder, leading to improved performance. A case study illustrates the effectiveness of RLCoder in a real-world scenario, highlighting its ability to focus on meaningful candidates for code generation. The paper also reviews related work in code completion, including deep learning-based methods and the integration of large language models. In the paper, the authors propose a novel reinforcement learning framework for repository-level code completion, known as RLCoder. Unlike traditional methods, RLCoder does not require labeled data to train and uses a novel stop signal mechanism to know when to retrieve and which candidates to retain. The authors also introduce a simple yet effective split aggregate candidate construction method based on human programming habits. The proposed framework is evaluated on repository-level code completion and demonstrates good generalizability and applicability to further enhancing existing methods. The authors also provide a comprehensive review of related work in code completion, highlighting the strengths and limitations of various approaches. The paper's contributions include the development of a reinforcement learning-based code completion framework that iteratively learns by obtaining feedback from the evaluator, and the introduction of a novel stop signal mechanism and split aggregate candidate construction method. The authors also provide insights into the performance of RLCoder and discuss its potential applications and future directions. Overall, the paper presents a significant advancement in the field of code completion and has the potential to improve the efficiency and accuracy of code generation tasks. The provided pages detail a comprehensive overview of recent advancements in large language models, particularly focusing on their applications within the realm of software engineering. Several research papers are cited, each contributing to the understanding and development of these models for code generation, code summarization, and other tasks. The authors highlight the progressive learning approach proposed by Liu et al. 73, which involves teacher-student learning paradigms to enhance language model performance. Similarly, Hu et al. 74 present an approach for long code search using split, encode, and aggregate techniques. Liu et al. 75 conduct an empirical study comparing traditional programming with large language model support, emphasizing the potential benefits of using these models in software development. Wang et al. 76 introduce SparseCoder, a novel identifier-aware sparse transformer designed for file-level code summarization. This work demonstrates the capability of large language models in understanding and summarizing complex code structures. Zhou et al. 77 propose an adaptive solver framework that dynamically selects strategies for large language model reasoning, aiming to improve efficiency and accuracy. Furthermore, Shi et al. 78 discuss Sotana, an open-source software development assistant that leverages large language models to aid developers in various tasks. Zhang et al. 79 provide a survey on large language models for code, covering their evolution, benchmarking, and future trends. They also explore the understanding and application of these models in software engineering tasks. 80. The pages also touch upon the intersection of large language models with smart contract vulnerability detection. 81. Human-centric benchmarks for evaluating foundation models. 82. And recommending analogical APIs via knowledge graph embedding. 83. Moreover, researchers have been working on customizing large language models for code generation. 84. Improving domain-specific neural code generation. 85. And enhancing code completion using reinforcement learning. 86. In conclusion, The cited research papers collectively showcase the significant progress made in harnessing large language models for various software engineering tasks. These models are being explored for their potential to revolutionize code generation, summarization, and other aspects of software development, highlighting both their capabilities and the challenges that need to be addressed.